everyone. My name is Eric Cho, and I am from KGSEA Math Circle, and I'll be talking about the Pascal triangle. This is the Pascal triangle, even though Pascal wasn't the first person to discover it. Indian mathematician in the 10th century called it the staircase of Mount Meru. Iranian mathematicians of the 11th century called it the Cayenne triangle. 13th century Chinese mathematician Yang Hui also found it before Pascal in the 17th century. Just in case you guys don't know what this triangle is, I will explain how to create this triangle. First, we start with two diagonal lines of ones. And then we add these two ones to get a 2 right below them, like this. By doing the same action for the numbers in the next row, we can add 1 and 2 to get a 3. Doing this twice completes that row of numbers. By continuing this process, you will end up with the Pascal triangle. Please consider that the row with only 1, 1 is considered row 0. Also, just because this visual only has until row 6 does not mean that the triangle ends there. The triangle actually extends forever. Now I'll be going into the Pascal triangle's patterns and properties. There are many patterns that are hidden in the Pascal triangle. Some patterns that you can notice right away is that the diagonals right next to diagonals of 1 are diagonals of consecutive natural numbers. Another pattern that you can see is that the sum of all numbers in the row is always a power of 2. However, it's not any power of 2, but it's the 2 to the power of the row number. The first few would look like this. And the rest would continue the pattern. As you can see on the right, the power of 2 increases by 1 each row. The next pattern is that the alternating sums of all of the numbers in each row is 0. This relates to the fact that the Pascal triangle is actually symmetrical. One of the most intriguing patterns is that starting from row 1, if we see each number in the row as a digit of a larger number, we can find a power of 11. For example, when we look at row 2, the first 1 will be the 100th digit, and the 2 will be the 10th digit, and the last 1 will be the 1st digit, giving us the value of 121, which is 11 squared. There are numerous other patterns, such as diagonals that have triangular numbers and tetrahedral numbers. Another famous pattern comes out when you shade in all of the odd numbers. When you do this to thousands of rows, you will get a fractal called the Sierpinski triangle, which looks like this. Now we will move on to another property of the Pascal triangle, the binomial expansion. Each row's numbers corresponds to the coefficients of the binomial expansion of an expression x plus y to the power of n. N is the row number, and remember that the row with 1, 1 is considered row 0. When n equals 0, the expression becomes 1, which is row 0 of the triangle. When n equals 1, the expression becomes x plus y, which has a coefficient of 1 for both x and y. When n equals 2, the expression becomes x squared plus 2xy plus y squared, which corresponds to the numbers in the second row. Now we will attempt this practice problem. This is a fairly easy problem. It's a computation question. So When people generally approach this problem, they think about expanding it one by one. However, by using the Pascal's triangle, we can solve this in a much more simpler manner. We first draw a Pascal's triangle until the fifth row to find the coefficients of 1, 5, 10, 10, 5, and 1 in that order. We can create an expansion using a plus b and the coefficients that we just found. X plus y. And then we can substitute 2a to x and 3b to y. Powers of 2 decreases as we move from left to right, while the powers of 3b increases. After simplifying, we will get this answer. Although the computation might not have been the easiest, it would have been much harder to expand this expression without using the Pascal triangle. This leads us to the topic of combinatorics in the Pascal's triangle. Previously, we have seen that the numbers on the Pascal's triangle are from the binomial expansions. We can actually find combinatorics during this process of binomial expansion. Each term is determined by choosing either a or b of a plus b n times. For example, when looking at x plus y to the power of 5, to get the coefficient of x to the power of 3, y to the power of 2, we need to choose 3 out of a, b, c, d, e to pick x, and 2 out of a, b, c, d, e to pick y. We can manually count all of them. After counting for all of them, we can see that there are 10 possibilities. We can also represent this in combination notation. Since out of 5 sets of x and y, we choose 2y, we can call this 5 choose 2. We don't need to think about choosing the 3 x's because after choosing 2 sets to pick y, there would only be 3 sets left to choose the 3x. The vice versa would work to come to the equivalent conclusion of 5 choose 3. By knowing that the numbers on the Pascal triangle can be written in this form, we can change the Pascal's triangle to this. Now going back to how the Pascal's triangle was formed, we know that the numbers on the Pascal triangle are the sum of the 2 numbers above. We can show this using combinatorics. We can easily show this by using Pascal's identity. Pascal's identity is what is on the slide right now. Pascal's identity is n choose k is equal to the sum of m minus 1 choose k minus 1 and m minus 1 choose k. The proof of Pascal's identity is very simple. First, change the combinations into factorial form. Then group both terms by m minus 1 factorial. After simplifying, multiply the n minus 1 factorial to the simplified fraction. The newly calculated fraction, when changed to combination notation, is n choose k. We can test this out by plugging some numbers in. When looking at 4 choose 2 and 4 choose 3, we can substitute these into the Pascal's identity. Just like we thought, we got 5 choose 3. Another popular identity we can get from the Pascal's triangle is the hockey stick identity. This identity can be seen twice on this particular Pascal triangle. Looking first at the blue colored numbers, the 3 diagonal blue numbers, 1, 4, and 10 add up to the highlighted blue number of 15. Now looking at the red numbers, the diagonal numbers of 1, 4, 10, 20, and 35 add up to the highlighted number of 70. It is called the hockey stick identity because, as you can clearly see, it looks like a hockey stick. Yeah. The equation for this identity is on here. If we look at the red numbers again, for example, this would be the case when n equals 7 and r equals 3. Now we will try solving this practice problem. This problem is the 12th question of the 2015 AME 1. The question reads, consider all 1000 element subsets of the set 1 through 2015. From each such subset, choose the least element. The arithmetic mean of all of these least elements is P over Q, where P and Q are relatively prime positive integers. Find P plus Q. Now we can come up with an equation to find the total sum of all of the least elements. This equation simply multiplies the least element to the amount of subsets that has that least element. This is the equation. This equation can be expanded due to multiplication being repeated addition. Now we can use the hockey stick identity to simplify each row. We just need to find the sum of all of the rows now. We can use the hockey stick identity again to simplify it further. After a bit of calculations, we can find that x is 288 over 143, leading to the answer of 431. This is the end of the lecture on Pascal's triangles. I hope that you guys have all learned something new about the Pascal triangle, whether it be some properties, identities, or uses. Although this lecture included mostly information, I hope that this lecture has made you guys more interested in the beauty of the Pascal triangle or math in general. There are still many properties and mysteries about the Pascal triangle that I did not discuss, including most notably the Fibonacci sequence. I hope that you guys have all found a spark of interest to continue exploring the different wonders in the mathematical world. Thank you.